our landmark building, and our vision is to be a dynamic cultural center for community learning. This program is part of our Monday Enrichment Series, thanks to our science sponsors, Susan and John Kelty, and Ted and Joanne DePotis. I'm Mila Tellez, member of the Science Program Committee. We're fortunate to have Dale Jones as our speaker today. Dale is an expert on energy generation. He has a BS in engineering physics from the University of Maine. Upon graduation, he worked at the Knowles Atomic Power Laboratory, operated by GE for the U.S. Navy. He was a civilian operator at a nuclear submarine prototype used to train U.S. Navy submarine crews. Following qualification as an engineering officer of the watch, he remained as an operator and instructor. Next, he moved to combustion engineering, which was one of 3 main domestic suppliers of nuclear reactor systems for use in commercial power generation. He was involved in developing and implementing nuclear safety system test programs to comply with nuclear plant licensing commitments and Nuclear Regulatory Commission regulations. Most recently, he has been a project manager on projects involving electrical distribution in and around the city of Chicago. Extra energy needs for AI and crypto. Dale is going to enlighten us on power generation for a reliable energy future. Please welcome Dale.
Well, after that nice introduction, well, let me start off with the title of my talk, Power Generation for a Reliable Energy Future. Does one size really fit all? And I think you'll see what I mean as we get into the presentation. Since one of the most debated topics in recent times is energy, particularly the generation of electricity. It seems almost everyone has an opinion as to which methods of providing electric power to our homes and industries are the safest, cleanest, and cheapest. I hope the information I share with you today will help you wade through the noise, and there's a lot of noise. Generation and use of electricity is critical to our economy and the economy of the world. Use of energy is a key driver of economic growth and industrial development. Electricity production for personal and industrial use has an impact on the environment through the discharge of environmental pollutants, both chemical and thermal. I will review the different types of generating sources available and currently in use, along with the pros and cons of each, and I will describe some we expect to be available soon. These sources make our everyday life comfortable and are necessary for the functioning of the industries that supply the products like food and medicines that we rely on every day. While energy sources that are used in our homes and industries are varied in their source and use, for example, natural gas, heating oil or electricity can be used to heat our homes. Gasoline or electric storage batteries can be used to operate our trucks and automobiles. I'm going to concentrate today on the generation and use of electricity. The first electric motors and generators were developed by Michael Faraday and Joseph Henry. The first DC electrical distribution system was built by Thomas Edison in the mid-19th century. How appropriate for the 19th century club. Soon, AC electrical distribution systems were developed that allowed the transmission of electrical power over long distances and resulted in amazing economic growth and prosperity starting in the late 19th century and exploded during the 20th and the 21st century. So let's start with demand. According to the U.S. Energy Information Authority, electricity consumption in the U.S. entered a period of growth in 2025, following a period of relatively flat electricity demand from the mid-2000s and extending into early 2025. Since then, many experts have warned that the increase in demand for electricity could be significantly larger by as much as double or even triple the 2024 projected rate. Even if the increases are in line with the EIA 2024 projections, the increase is still significant. The increased demand will put stress on our electrical infrastructure. Over 70% of transmission lines, which are designed for a 50 to 80-year lifespan, are more than 25 years old. Extreme weather events like the recent polar vortex put significant stresses on our electrical supply system. According to a recent editorial in the Wall Street Journal, Midwest utilities had to request that customers turn down heat and hot water thermostats while fossil fuel powered plants were issued emission rule waivers so that they could meet the power demand. At the peak of the weather emergency, 40% of the electricity in the Midwest grid was supplied from either coal-powered plants, with the rest coming from natural gas or nuclear. Okay, so why is electricity demand increasing? The 500-pound gorilla of current demand stress is the proliferation of data centers, which I'm sure many of you have heard about. According to some experts, this could contribute as much as 44% of the growth. There's also a resurgence in manufacturing since COVID and the resulting trend of bringing more manufacturing onshore to the United States. Increased use of electric vehicles. I know many of you people probably do drive electric vehicles, and you charge them every night. Well, that's an additional stressor on the system. Converting more home heating oil from natural gas and home heating oil to electric heat and replacing gas appliances with electric appliances. Conversion of industrial processes from fossil fuels to electric are all stressors on the system and require our action. So what's to be done? For my research, I think the following steps, many of which are currently being taken, can ease the impact of our expanding electricity needs. First, we must modernize our aging transmission and distribution system. Although none of us wants to pay any bigger electric bills, we want to convert more of our homes to industrial equipment to electric, and we want to drive electric vehicles and charge our electronics devices. So we must pay to upgrade the distribution system that transmits that electricity. This includes the construction of the necessary new transmission lines, which should include the installation of protective equipment, such as the neutral blocking devices. How many of you recently saw the press about the sunspots? Well, sunspots result in solar flares, and solar flares are a hazard to our electrical distribution system. But there is a solution to that. It just takes a little bit of money and not a lot of money, and they're called neutral blocking devices that protect the grid components from solar storms like the ones that we recently experienced. Large new data centers and other industries that represent big increases in demand should pay in advance for the necessary distribution system upgrades needed to supply the load they're adding to the grid. A little bit more on that later. Some states and federal governments are considering legislation to require large data center owners to provide their own power off the grid. Permitting for new distribution system construction should be streamlined to cut costs and to speed them up, and those who tend to oppose this work should reconsider the benefits of these improvements may bring to the entire community. A mix of new generating facilities are required to meet the need for additional power and reliability. As I hope to show, no one size fits all when it comes to generating electricity. Okay, let's talk a little bit about electrical distribution. In the early 70s, one of my favorite engineering professors at the University of Maine used to say that electricity would be quite inexpensive, almost free, if you could carry a bucket to the power plant, open a spigot, and fill it with electricity, paying for only what you take away. Why does electricity cost so much? Are the utilities cheating us? What he told us then is still true today. A large part of the cost of the electricity that you pay is due to the need to deliver the electricity to the specific location where you want to use it, and to make sure that when you flick your switch, your lights will come on, or your washing machine will start, and your electric cars will charge up overnight. Getting it from its source, whether that be a coal or nuclear plant, a hydroelectric dam, a wind farm, a solar farm, requires that utilities install long, heavy wires called transmission and distribution lines to carry the electricity from the generator or other source to the point where you want to use it. The longer the lines, the greater the losses due to resistance heating of the wires, switches, and connectors that make up the distribution system. For reliability, the transmission system from the various sources are interconnected to form what we call a grid. And the grid is interconnected over the entire nation. I didn't spend any time going into grid constructions, but it's very interesting, and you may want to look that up if you have a chance. But everything from Maine to California to Alberta and Canada and Quebec. These grids are all interconnected so that they can transmit electricity from one area to another to try to control the load and make sure that everybody has a continuous supply. So let's talk about the components of the grid. There are two major sections of the grid. If you look at this diagram, the red and blue sections are what we call the bulk energy system. The red is where the power is generated, and the blue is where it's transmitted from the generating station to where it's needed. Okay, and it's stepped up from the generating source to anywhere from 135,000 volts to 765,000 volts. As I said earlier, this makes for more efficient transmission and less loss. When it gets near to your home, it's stepped down to a lower voltage. And the step down can be as low as can be from 26 kV, 69 kV. That's for businesses like a large factory. If you have a car plant in your neighborhood or something, they use a higher voltage than you use in your home. And then when it comes along the top line on your pole behind your garage, okay, and then pops down to a little cylindrical transformer, it's stepped down to 120 volts and 240 volts. And so that's how it gets from the plant to your reading light. So who's responsible for grid operation? Interstate transmission and wholesale of electricity is regulated by the Federal Energy Regulatory Commission, commonly known as FERC. The power grid is divided into three major sections: the eastern, the western, and Texas. Everything's big in Texas. Within the three major sections, the flow of power is controlled by the regional transmission organizations, RTOs, or independent system operators. And the local operation is the responsibility of the local utilities and the state utilities commissions. Current sources employed to generate electricity. Perhaps most controversial issue that we face due to the expanding demand for electrical power is how to generate it. Most forms of electric power generation require an energy source to operate a mechanical generator. The basics of electrical generators have not changed since the first electric power generators built in the late 19th century. They involve a rotating electrical conductor, usually coils of wire, surrounded by a magnet, usually an electromagnet. The moving conductor in the magnetic field causes an electric current to be induced in the wire, and this was first described by Joseph Henry, an American scientist, and Michael Faraday, a British scientist, right around 1830, 1831. There's a little bit of controversy over who was the first. It's generally believed that Joseph Henry, the American, who was at Princeton at the time, was the first, but Faraday was first to publish, so he gets credit. While the design of the generators has remained basically unchanged, the various means of providing the mechanical energy to run the generators have changed significantly. This is where the controversy lies. What is the best way to run the generator? If you're thinking about solar cells, they don't use traditional mechanical generators to make electricity, so you would be correct there. The major sources of electricity that we deploy today are shown in the table at the left. The data is the latest I could find, and it's for 2023, and I expect that the current mix is the same. As you can see, the largest amount of power is provided by fossil fuels. About 60% of the power we use is fossil fuels. Natural gas about 43%, coal about 16%, petroleum 0.4%, and other sources about 0.5%. Next on the list is nuclear power at 18%, and then renewables at 21%, 10% wind, 4% solar, that's both PV, photovoltaic and thermal, hydropower, biomass, and geothermal. And I thought I'd put up this chart because some people like visuals, and this kind of shows you how the various mix of generation has changed over time. The brown being coal, the let's look at the green being renewable. Oh, I'm sorry, this brown being coal. Okay, this is natural gas, this is nuclear, this is renewable, and then this is petroleum. Okay, just a little tutorial for those of you that might be interested. Well, we generate electricity pretty much the same way, regardless of the energy source. The most common way is for fossil fuels, geothermal, nuclear, and solar thermal, is we generate heat, we make steam. Steam turns a turbine. The turbine turns an electrical generator, and out comes electricity. In the case of hydroelectric, we have a dam or a large reservoir that runs water through a hydroturbine, which is not unlike the steam turbine, but it's turned with water rather than steam. That's hooked to an AC generator, and out comes our electricity. It's a relatively simple process, although the equipment can be fairly complex. Then we get into wind. Wind is not that unlike the others. Wind turns a big propeller. The propeller is hooked to a small DC generator. The DC generator then produces DC current, which it runs through a device called an inverter, which changes DC to AC. And then we have solar photovoltaic. That's where the sun hits a solar cell. It generates DC electricity. That also must be run through an inverter to turn it to AC, so it's useful to us. New electric power plants, what's needed? What are the requirements when we will decide that we're ready to build some new generation? The critical considerations when selecting new power plants are, first, application. Will the plant be supplying large amounts of electrical power on a continuous basis? It's what we call base load. Or is it being constructed to cover changes in demand, which we call peaking units, or interruptions due to equipment failure or damage to other generating sources due to weather or natural disasters? Let's talk a little bit about baseload. Baseload plants should operate 24/7 because they take too much time and effort to start up and shut down. They typically have lower fuel costs than peaking units. They are capital intensive to build and to cover their costs, and they should operate continuously to maximize the revenue they generate. Examples of baseload: nuclear, coal are probably the two biggest. Peaking plants. Peaking plants can start up and shut down quickly. They often have higher fuel costs, so they are run as needed to cover shortfalls in demand, such as when baseload plants are shut down for repairs or refueling, or to make up for intermittencies in renewable sources like wind and solar. Typically used for peaking load are gas generators, natural gas generators. Accessibility. Are there sufficient transmission and distribution resources to get electricity from the plant to the user? We must be able to count on the plant to provide power where we need it. Reliability. For our economy to provide a good standard of living for everyone, we need an electrical generating and distribution system that can be counted on to supply baseload of electricity 24/7 and peaking power where and whenever we need it. In some parts of the world, electric service is expensive and intermittent at best. We need both baseload and peaking plants to assure reliability. The same types of plants don't serve both functions. Again, that was my point with one size does not fit all. Reasonable cost. Just after World War II, some optimistic proponents of nuclear energy said it would be too cheap to meter. Well, that never happened. The relative costs of the various power sources are a major factor in choosing which mix of generating types are best in the region where the power is needed. These costs include the capital cost of the plant itself, the cost of fuel to run the plant, the environmental impact of the plant, and particularly for some types of renewables, the proximity to the energy source or the end user. Environmental impact. When new generating capacity is needed, sources that have the least negative total environmental impact, and this includes looking at the whole supply chain, a little bit more about that later, while still meeting the application, accessibility, reliability, and cost requirements should be chosen. Okay, so now we're going to talk a little bit about pros and cons. Okay, we're going to start with coal. Coal has low cost and is abundant. It's an efficient means of power generation. Coal plants are reliable and can produce electricity 24/7. They're good baseload supplies. Coal mining and transportation produce abundant jobs. Due to high energy density, land use is small for the power produced. It requires less land than other generating sources currently being employed. They require about 15 square meters of land per megawatt hour produced. What are the cons? Coal, although abundant, the supply is limited. It's not renewable. Coal burning produces atmospheric pollutants and carbon dioxide. Coal mining can pollute the land and water. Next is natural gas. Natural gas emits 50% less CO2 than coal and 30% less than oil, as well as less of other pollutants. High efficiency means power generation is efficient. Natural gas reserves are abundant. Natural gas plants can ramp up and down rapidly in response to changes in demand, and so are a good partner for renewable sources that can experience sudden changes in output. So they're good peaking as well as baseload plants. Due to high energy density and land use, the land use is small for the power produced, approximately 1 square meter per megawatt hour. Still produces some CO2 and airborne pollutants, a significant source of methane, which is a potent greenhouse gas. Extraction and processing can also contribute to air and water pollution. Hydropower doesn't pollute the water or air. It's renewable, reliable, flexible, but it can be a high land use. When you build a big dam, you use a lot of land to do that, and you also cover up a lot of land with the ponds, the lakes that you create behind them. For a large plant, and the land use is even worse for smaller hydro plants than it is for larger hydro plants when you break it down on a per megawatt hour basis. The cons may change the temperature of the flow of the water, may cause low levels of dissolved oxygen in the water, disturbs river habitats and fish reproduction, has a high capital cost, and it can be affected by droughts. The next one is wind. It's clean and does not pollute. It's renewable. It has a low operating cost, low land use, about 0.4 of a square meter per annual megawatt hour. This assumes that you're putting it like in a cornfield or something where the land it takes up is only the one that the tower is actually sitting on, and that the land around it can be used for other uses. It's intermittent and unpredictable. It works only when the wind blows, and we can't necessarily predict that. It may result in the death of bats, birds, and possibly whales for offshore installation. It has a high upfront investment, and they're noisy. There's a lot of noise and visual pollution. The people in Martha's Vineyard did not want a wind farm put outside their island. I don't know if you remember that controversy from a while ago. Solar photovoltaics. They're abundant and renewable, sustainable, approximately 12.6 square meters per megawatt hour. This we're referring to solar farms that are on the land, not solar cells that are on top of your house. They do not pollute the air or water. They're silent and they're low maintenance. They contain solar cells which require expensive rare materials such as copper, indium, gallium, selenide, cadmium telluride. This is one that the next one is one that I didn't know before I prepared for this presentation. Solar panel production emits hexafluoroethane, nitrotrifluoride, and sulfur hexafluoride, which are very potent greenhouse gases. Now, they don't produce them where the solar cells are sitting in the farm, but over in China where they're building the solar cells and building the panels that they're sending over here, they're releasing these greenhouse gases. And you know, it's all part of the same atmosphere, so it's something that should concern us. And this is what I was talking about when I said, when you're talking about environmental impact, you need to look at the whole supply chain, not just the point where the plant is being placed. It requires large amounts of land space, approximately 12.6 square meters per megawatt. Geothermal. Advanced systems don't release gases to the air. They rely on closed-loop designs and reinjection processes. They create small amounts of CO2 and sulfur components, smaller amounts of CO2 and sulfur components than fossil fuels. Its use does not burn fuels. Reliable and predictable source of energy. It makes a good base load. Renewable resource, with exceptions, and we'll talk about that in the con section. Other plants can emit hydrogen sulfide, carbon dioxide, methane, and trace amounts of heavy metals from deep underground. Can be mitigated through the use of scrubbers and capture harmful emissions before they are released to the atmosphere. Can be done, adds to the cost. Closed loops and scrubbers add significant cost to the newer plants. High capital cost and possible induced seismicity, which can occur when fluid is re-injected into the underground to stimulate the reservoirs. They're highly location dependent. You can't put up a big geothermal plant anywhere. Good example is Iceland. Iceland has a lot of geothermal activity. My wife and I were just there a couple of years ago. Just about all of their power in Iceland is being provided by geothermal because they have a lot of volcanic activity. Okay, Northern California has a number of geothermal plants because they have good access to the type of geothermal activity that makes them good. But they probably wouldn't work in the Arabian Desert, for example. High upfront costs for drilling. Locations can suffer from thermal drawdown if hot water or steam is extracted faster than it is replaced. This can be partially mitigated by reinjection. High upfront costs for drilling, geological surveys, and environmental assessments. A promising site may fall short in actual energy output due to unexpected changes in temperature, water flow, or underground rock composition. Nuclear. It's an insignificant carbon emissions, more efficient and reliable than fossil fuels. It's a very, very good baseload. Low operating costs. I bet you didn't believe that, but it's true. Requires less land than any other generating source currently being employed, about 0.3 of a square meter per megawatt hour. In the last 60 years, with over 18,500 cumulative reactor years in 36 countries, there have been only 3 significant accidents, excluding Chernobyl. There have been no loss of life. That's 0. High construction startup costs. Uranium is cons. High construction startup costs. Uranium is a finite, non-renewable resource. Security may be an issue and may be a possible target for terrorists. The high amounts of water for production of the steam and cooling systems are required. Nuclear accidents could pose a serious health effects. New reactors have inherently safe designs. A good example of a badly designed, badly operated plant that can result in serious health effects, of course, is the one we're all familiar with, Chernobyl. Okay. Last slide is just kind of a summary of the land use for the various different types of electricity generating that I just talked about. Hydropower, less than 360 megawatts. Solar thermal. I didn't really talk much about solar thermal, but a solar thermal plant is a plant like they recently had out west, where you have a tall tower with a boiler on the top, and then you have a series of mirrors that surround it in a big circle, and they focus the sunlight up to the boiler, generate steam, use that steam to run a traditional steam turbine, and which is hooked to a traditional generator. If you've been following the news on this one, you'll find, however, that the utility that was running that one in California has decided that it wasn't economically viable, and they're dismantling that one. And there are maybe a half a dozen sites like that around the world currently. Coal with carbon capture, 21. Solar photovoltaic. Hydropower, large hydropower projects. Natural gas. Wind, and down here at 0.3 is my friend, nuclear. Breaking news. I told you I was going to talk a little bit about the cost, and this just occurred this week, March 4th. President Trump and tech executives from Google, Meta, Oracle, xAI, OpenAI, and Amazon signed the Ratepayer Protection Pledge. The pledge has 5 aspects that will protect ratepayers from ballooning electric rates while supporting the development of AI technology in the United States. The 5 aspects of the pledge are building, bringing, or buying new power supply. And let me read what we're talking about there. Companies will build, bring, or buy new generation resources and electricity needed to satisfy their new energy demands, paying the full cost of those resources, whether by building or buying them. New or otherwise additive power plants. Where possible, these companies will also add more capacity that serves the broader public by increasing supply. Paying for new power delivery infrastructure upgrades. Companies will pay for all new power delivery infrastructure upgrades required to service their data centers, including adequate network upgrades, costs to ensure that these expenses are not passed on to ordinary households. Paying whether they use the power or not. Companies will voluntarily negotiate new, separate rate structures with their utilities and relevant state governments wherever they build data centers. Importantly, they will pay these rates for the power and related infrastructure that they brought online to service their data centers, whether they use the electricity or not. investing in local job creation and workforce development. Companies that will invest in the local communities in which they build data centers. This includes hiring from within the local community and establishing programs to develop relevant skills. I happened to see the news conference from the White House where this was announced, and the CEO of Meta announced that with the data center that they're building down on the border between Arkansas and Tennessee, that they're building a new education center to train electricians and technicians to do fiber optic connections and whatnot. And they were going to train, I don't remember the number, but it was several hundred people to have those skills, and they were committed to employing all of them. Contributing to electric and community resilience. Companies will coordinate with grid operators to contribute to a more reliable grid, and whenever possible will make available their backup generation resources at times of scarcity to prevent blackouts and power outages in their communities. Starting in the early 1950s, the U.S. Navy under Admiral Hyman Rickover developed the pressurized water reactor, or PWR, for the Navy, particularly submarine use. The first commercial nuclear power plant in the world was in Shippingport, Pennsylvania, and went into operation in December of 1957. According to the U.S. Energy Information Authority, there are currently 54 operating nuclear power plants in the U.S., consisting of 96 nuclear power reactors, of which 63 are pressurized water reactors and 31 are boiling water reactors. According to the Nuclear Safety Administration of China, they have 59 operating nuclear power plants as of January 5th of 2026. According to the Wall Street Journal on December 10th of 2025, China has 34 nuclear reactors under construction and 200 more planned. The United States has 0 commercial power plants now under construction, and according to Westinghouse, 10 are planned by 2030. So you can see the Chinese are all in. Okay, so let's talk about nuclear fission. I'll give a little tutorial here for any of you guys that might like to know what's going on with that, if you don't already. Nuclear fission occurs when a neutron is absorbed by a uranium nucleus, causing the nucleus to enter an excited state, then causing it to fission or split into 2 nucleons, fission products, along with 2 to 3 neutrons and gamma rays. The kinetic energy, which is the energy of motion of the neutrons and the lighter atoms, plus the gamma ray energy, produces heat. That heat we use to make steam that runs to the electric steam turbines and the electric generators. What's needed for nuclear fission? In order to produce power in a nuclear plant reactor core, we need self-sustaining fission chain reaction. This requires 2 things. The first is sufficient uranium-235 to initiate and sustain a chain reaction. Most of these operating commercial nuclear power plants in the United States have light water reactors fueled with enriched uranium at 3% to 5%. The 2 newest nuclear plants in the country are the Alvin W. Vogel Units 3 and 4, and they're fueled with the newest type of nuclear plant fuel called HALEU, which is enriched to 6%. HALEU stands for high assay, low enriched uranium. Now, I kind of put this in here because there's been a lot of talk lately with a situation in Iran about enrichment and about will we let the Iranians enrich or will we not? Okay. Well, the enrichment that the Iranians were doing were 60% and above. It takes an enrichment of close to 90%, 80 to 90% in order to make a bomb. And they were well in excess of just the 3 or 5% you need to run a nuclear reactor. So the argument that they were just enriching uranium because they wanted nuclear power is highly questionable. We also need enough slow thermal neutrons to maintain the chain reaction. Since the neutrons produced by fission reaction are nearly all fast neutrons, that means greater than 2 million electron volts, which is real fast, okay, it is necessary to slow them down to thermal energies, which is about 0.025 electron volts. Not very fast. That's where light water, which is just another name for tap water, comes in. Water acts as a moderator. which means that it is very effective in slowing neutrons down from the energy they are produced during fission to thermal energy. The water also acts as a coolant in the reactor and transports the heat to the steam generators for making steam. That was one of the reasons why, when Admiral Rickover developed the first nuclear plants, they chose water to use, because it's not only a good heat transfer mechanism, not the best, but a good one, and it also acts as a moderator. If you use a better heat transfer mechanism in your loops to run to your steam generators, like molten sodium, okay, you need something else to moderate the neutrons produced in the reactor. Typically, carbon is used. Reopening retired nuclear plants is another way we can restore get some of the power we need. One of the ways we can expeditiously add generating capacity to the system is to restart nuclear power plants that were shut down and are being decommissioned for economic reasons. Recently, 3 such plants are pursuing authorization to restart and extend their operating licenses. The 800-plus megawatt electric Palisades nuclear plant, located in Covert Township, Michigan, near South Haven on Lake Michigan, is undergoing updates and licensing to reopen. The plant was closed in May 2022 for financial reasons. In September 2022, a power purchase agreement was reached with Wolverine Power Corporation and Holtec International to reopen the plant. Holtec received funding from the state of Michigan and loan guarantees from the DOE for the project. Restart is planned for 2026. Holtec is also considering setting 2 small modular reactors at the site. The next one is the Duane Arnold Energy Center. Nextra Energy has filed with the NRC to restart the 600-megawatt Duane Arnold Energy Center near Palo, Iowa, as a power source for new data centers to be constructed in Iowa. The plant ceased operation in August 2020 following damage to its cooling tower by a derecho. The rest of the plant remains in good condition. 3 Mile Island Unit 1. Constellation Energy, which is the nuclear arm that was spun off from ComEd, okay, and has since added a lot of other nuclear plants to their stable. Okay, so they own Byron, Braidwood, LaSalle, Quad Cities. Constellation Energy, the owner of the 837-megawatt electric 3 Mile Island Unit 1, renamed the Crane Clean Energy Center, has entered a power purchase agreement with Microsoft to reopen Unit 1, which was not damaged by the March 1979 accident at Unit 2. A little bit about safety. Okay, I'm going to kind of go into what may seem like an esoteric discussion, but it kind of gives you an idea on how we determine the safety of a nuclear power plant that we're getting ready to build. The NRC and the utilities use something called probabilistic risk assessment. It's a methodology used to calculate likelihood of a serious event taking place in an engineered system, and it's used to assess risks in nuclear power plants. It's not just used in nuclear power plants, but any large engineered system. The NRC requires that reactor designs meet a theoretical core damage frequency of 1 in 10,000 years. However, U.S. utilities require their design to meet a core damage frequency of 1 in 100,000 years, with the best operating plants meeting a value of maybe as much as 1 in 1 million years. I'll repeat something that I said earlier, because I wanted to make the point. In 18,500 cumulative reactor years in 36 countries, there have been only 2 major accidents resulting in release of radioactivity. That's Chernobyl and Fukushima. Note, at 3 Mile Island, the maximum dose at the site boundary was 100 millirem, which is about the amount you receive from a chest X-ray. Aside from Chernobyl, not one single death has been attributed to an operation of a commercial nuclear power plant, a safety record no other industry can match. Generation 3 reactors represent a significant evolution to our current power plant reactors. They are generally designed to produce about 1,000 megawatts or more and have simpler standardized design that can be built in less time and less cost with expedited licensing. Simpler, more rugged design which makes Generation 3 reactors easier to operate and less vulnerable to operational upsets. Longer lifespans, which is expected to be around 60 years. Reduced probability of accidental core damage. Estimated core damage frequency of 5 times 10 to the minus, I can read it, 6th, which is about 1 core damage causing accident per 200,000 years. Following a reactor shutdown, typically no active intervention will be required for a Generation 3 reactors. That's 72 hours. You can walk away from the plant, come back after 72 hours, and then maybe you might have to do something, maybe not. Fuel burnup is higher, resulting in more efficient operation and less waste. Generation 3 reactors were first built overseas. They have some, I saw a recent YouTube video showing the one that was completed not too long ago in Finland. Generation 3 reactors were first built overseas and have 2 completed Generation 3 reactors operating in the United States. You have the Alvin W. Vogel Electric Generating Plant, Units 3 and 4, located in Burke County near Waynesboro, Georgia. Small modular reactors. Small modular reactors, or SMRs, are advanced nuclear reactors that have a power capacity of up to about 300 megawatts electric, which is about 1/3 of the generating capacity of a traditional power reactor. The picture I put up here is one of the small modular reactors that has currently been licensed by the NRC. One like this is being planned for several locations at the Tennessee Valley Authority, and there have been some built overseas as well. And as you can see, each of these little bays is a separate reactor. Okay, so they're small reactors that you can put in one at a time as your power needs increases, or you can take them out. And they're all light water, low-enriched uranium reactors, the type of reactors we have a lot of experience with, and they're designed such that they can be cooled using natural circulation flow to not require the external engineered systems of high-capacity pumps and so forth that are required for the earlier Generation 2 and below reactors that we currently have in operation in most places. Microreactors. Microreactors are a category of SMRs that are designed to generate electrical power typically up to 10 megawatts electric. Microreactors have a smaller footprint than other SMRs and will be well suited for regions inaccessible, to clean, reliable, resilient, and affordable energy, including remote areas where large utility grids are not in place or the delivery of fossil fuels is cumbersome. And again, on this picture, I'm going to talk a little bit about this later. This is the E. Vinci reactor, which is being produced by Westinghouse. This is a microreactor. This is just a flatbed truck. Okay, and this is the way the reactor comes from the factory, all ready to mount, plug in, and go. And this is seriously being considered by a lot of industries to run remote projects and by the military. Benefits of small modular reactors. The first one is modularity. The major components can be fabricated in a factory and shipped to the point of use. Assembly is simpler, requiring much less construction time than conventional nuclear plants. Additional modules can be added if energy needs increase. They have lower capital investments, smaller size, ease of construction, and ability to add additional modules will reduce the owner's capital costs. Siting flexibility. SMRs can provide clean, zero-carbon power closer to the location of the need, and if the area is isolated with a limited water resources and land available to construct power plants. In parts of the world, such as Indonesia, where towns and villages are on remote islands with inadequate space for power plant construction, they are considering placing SMRs on boats that can be sailed to the island and attached to the local grid. Greater efficiency. SMRs can be coupled with renewables to provide continuity of electricity. When the renewables are unable to supply the needed power, they can also provide heat for heating homes and buildings in frigid climates like they're currently doing in Finland, or for other industrial applications. Safeguards and security. SMRs are engineered to be inherently safe from nuclear accidents and can operate for extended periods of time without the need for refueling. Economic development. SMRs will help us to meet our ever-growing need for new sources of energy to operate our factories and data centers. Here's one you might be interested in. This is a small modular reactor that is about to be built in Champaign, Illinois, at the University of Illinois. Okay, this is a Kronos mini micromodular reactors being produced by Nano Nuclear. Okay, they've gotten pretty much the go-ahead. They're just completing the site surveys that they need to now. In my research, they expect to be going for a construction permit early this year. It's going to be a helium gas-cooled reactor, moderated, graphite moderated, and using low enrichment uranium triso fuel. It'll be about 45 megawatts thermal. Well, what are they going to use it for? They're going to use it to heat the campus buildings. Molten salt provides heat transfer to the campus steam plant, campus heating, and may be used to generate electricity as well. Site testing, I said, is currently in operation, and they're expecting to go to the appropriate authorities to get a construction license issued sometime before the middle of the year. Westinghouse eVinci microreactor, that's the one I showed you that was on the back of the flatbed truck. Okay, they are about 5 megawatts electric, enough power for about 2,000 to 5,000 homes. They're fueled again with the triso fuel. They arrive on site via rail, barge, or truck, fully assembled, less than 2-acre footprint, and requires minimal on-site personnel to operate and maintain. Can load follow, so it's easy to be paired with renewables such as wind and solar. For those of you that don't know what load following means, that if the load on the grid, in other words, say if a big customer somewhere else goes off the grid and the demand for the amount of electricity on the grid goes down, the reactor will automatically reduce its power too to kind of maintain continuity. It also works in the other way. If you've got a bunch of new loads that automatically get added on and the demand goes up, it can ramp up and provide that additional needed electricity. They replace about 55,000 tons of CO2 compared to fossil fuels to generate the same amount of power. They have redundant and passive safety features. Heat pipe technology eliminates the need for liquid coolant and pumps. Shutdown rods inserted during transportation are available as a redundant shutdown method. Control drums control reactivity and passively rotate to shutdown position during a shutdown. Decay heat removal is passive via natural convection and radiation heat transfer. No operator action required. And I've got a little video that I'm going to show you about that I think you'll find very enlightening.
Meet the eVinci microreactor from Westinghouse, a breakthrough technology that will make clean and constant energy possible anywhere. Constructed and fueled in a factory, these nuclear batteries are smaller than a school bus and live inside compact, above-ground facilities. They can power towns, data centers, military bases, mines, or oil and gas facilities continuously for decades, swapping in fresh reactors about once every 10 years. Inside the core, a uranium-based fuel with built-in protective layers powers the nuclear reaction. Then, heat pipes channel that energy out of the core, where hot air is converted into a steady flow of electricity. Today, teams of Westinghouse engineers are already bringing this vision to life. Join us to create a cleaner, more sustainable world.
But if you kind of look at this, one of the cool things about it is you see in behind it on the drawing here is it shows it sitting in front of a school bus. So that's what it is. It's about the size of a school bus. Okay, and it provides enough to like say 8,000 homes or a small industrial thing, or it can be used on military bases, and it sits there and produces electricity for about 8 years, and then when it's near the end of life, another truck comes in with a replacement, they pull that one out, they plop the new one in, and they go for another 8 years. They take it back to the factory and refuel it. The next thing I want to talk about is the reactor pilot testing program. In June of 2025, the Department of Energy announced the creation of the reactor pilot testing program following the issuance of President Trump's Executive Order 14301, reforming nuclear reactor testing at the Department of Energy. The program is designed to accelerate development of testing of advanced nuclear reactors. 10 companies with advanced reactors in late stages of development have been selected to participate. And this is a list of companies that are participating. The main aspect of this is that the federal government has made testing sites and land available on government reservations like Idaho and Utah, which have been used for military testing, and they're making them available to commercial companies to bring in and test their reactors, work the bugs out to speed their completion and availability for use commercially. One of those companies on that list was a company called Valor Atomics, and I just put this one on as an example, and it's also kind of interesting. Okay, it's going to be tested at the Utah San Rafael Energy Lab in Utah. Interesting thing, if you happen to see the papers, on February 17th, the Department of Energy transported a Ward 250 microreactor to the Utah inside of 3 C-17 military transports to begin assembling and testing. So that's the idea. We need something in Diego Garcia to power our missile test facility out there. We load it on 3 C-17s, take it out there, hook it up, and we got power. The reactor type is a helium-cooled, triso-fueled, high-temperature gas SMR. Design output is about 100 kilowatt thermal, and it's being done under the DOE's nuclear reactor pilot program. Now let's go into nuclear fission. That's been getting a lot of attention lately. Nuclear fusion has been about 10 to 20 years away as long as I can remember. And I remember a while. I was in high school in the 70s. In college in the 70s. First net positive production energy from a controlled nuclear fusion, however, occurred at the National Ignition Facility in Livermore, California on December 5th, 2020. This was a big deal. Okay. The thing about fusion power is you have to put a lot of energy in order to get the reactor started. And once you put all that energy in and get the reaction started, the goal is to get more energy out than you put in. Because if you don't, then it's not worth the time. All right. Well, on December 5th, 2022, they had the first instance where they had ignited a fusion reaction that produced more power than it took to start. Oil and gas giant Eni has inked a $1 billion deal with the fusion power startup Commonwealth Fusion Systems to buy power from its fusion power plant in Virginia, even though the reactor does not yet exist. There's a lot of positive feelings out there, but we're not quite there yet. According to the Fusion Industry Association, over $2.5 billion of public and private funds have been invested in fusion power projects so far. When asked why more energy seems to be going into a new fusion projects than fission projects, Matt Lozak, CEO of ALO Atomics, one of the ones in the list that I showed you, said investors seem to be saying that, quote, it is easier to recreate the sun in a small box than convince the public that fission is safe. Nuclear fusion occurs when at least one heavier, more stable nucleus is produced from 2 lighter, less stable nuclei. Reactions of this type are responsible for enormous release of energy, such as the energy given off by stars. First commercial reactors are expected to be fueled with 2 isotopes of hydrogen, deuterium and tritium. The fuel will need to be heated to a very high temperature, greater than 100 million degrees Celsius. That's hotter than it is at the center of the sun, in order to initiate the fusion reaction. That's one of the reasons why this is so hard. And you can see from the little drawing, we get the deuterium and tritium join together, form a helium-4 nucleus, and then they kick off a helium-4 nucleus and a neutron, and the energy with which those guys go heats up the water. We make steam, we run our steam turbine, we run our electric generator, just the same as if we were heating the water with coal or natural gas. Types of nuclear fusion reactors. To achieve fusion reaction, the fuel must be maintained in a plasma state, which is a gaseous state where the atoms are separated into positive ions and electrons at high enough temperatures for long enough, which we refer to as confinement time, to cause the nuclei to fuse or combine, releasing energy in the form of kinetic energy and the reaction products, neutron and a helium nucleus. Converting this energy to electricity will be done by heating water to make steam and to power a turbine generator. There are currently 2 ways to create that little box, confinement, that Matt Lozak was talking about in that quote that I gave you earlier. The first way is magnetic confinement. Magnetic confinement uses strong magnetic fields to maintain the plasma in a confined space, which we call a magnetic bottle. Okay, so the plasma's in there floating inside, and the only thing that's keeping them from hitting the outside of the container are those magnetic fields, because they're so hot that if they hit the steel container in which they're in, they'd melt it. Okay? Which prevents loss of plasma ions to the surrounding structure, as well as causing damage to the structure from the high temperature of the plasmas. The other way is inertial confinement. I want to point out that inertial confinement was the method that they used at the National Ignition Facility that caused the first positive energy output from a fusion reaction. Inertial confinement uses large series of lasers focused on a fuel pellet. The radiation pressure confines and heats the fuel to the necessary temperature to cause a fusion reaction. So they've got this big machine where they've got these lasers and beam splitters, and they've got a little pellet of fuel, and they've got these lasers coming in from all directions. They hit the button, they all flash on at the same time. It produces so much heat and X-rays that it causes the fuel to fuse and release a lot of energy. And that's how inertial confinement works.
Could you go into a little bit more on the fusion, what the benefit and how much output it's going to produce?
Can I expound a little bit on the fusion process and how much more energy do we expect to get out of it than we put in? The general feeling is that it's going to be at least 4 to 5 times as much, okay, or more. But the true answer to that question is we've got to do it and sustain it first before we'll actually be able to measure the calorimetric know it's going to be.
Regarding the fission plants, what is the availability of the fuel, of the uranium, given the political situations all over the world and some of the major sources?
So there's quite a bit of uranium available, plus with some reactors, particularly the ones that are that I didn't really talk very much about, but use the fast neutron spectrum, they're going to be able to fuel with uranium-238, as well as uranium-235 to produce. Also, a lot of plutonium-239 is produced in these reactors, which right now, all we've been talking about is it. If we could turn around and reprocess that and use that, that's a very effective nuclear fuel.
I noticed that on the nuclear slide, pros and cons, it did not mention anything about the radioactive waste. So I know that we have to bury radioactive waste at some point. I'm just wondering what you think about that, because it's something that's very important that we're burying tons and tons of metric tons of radioactive waste in the state of Washington and in Idaho. So just wondering how you would not put that on your slide. Thank you.
There's a number of ways to deal or handle with nuclear waste. One of them is reprocessing. Now, we have not been reprocessing nuclear waste in this country for a number of reasons. Many of those reasons which are political, and some of them are fear of proliferation. The French and the Germans reprocess a lot of their spent nuclear waste and extract material that can be used to refuel reactors. Another one is that a number of these new reactors were being considered are what's known as breeder reactors. With a breeder reactor, you can take a blanket of, let's say, uranium-238 from a reactor that you've pulled out of the fuel from a regular thermal reactor, and the neutron flux from the reactor inside that blanket will convert that uranium-238 to plutonium-239. That plutonium-239 is also a very effective, easily fissionable fuel. So it's part of the answer to that is will. In other words, do we have the will to do the work and the reprocessing that's necessary in order to reuse that fuel? And I think now that we're getting into a period of time when a lot of these things were first said, well, we're not going to reprocess fuel, okay, we weren't real concerned about CO2. Now we're concerned about CO2, okay? So this nuclear power is one solution to the CO2 problem. So now maybe some of these other methods will be considered more acceptable. Another thing that these reactors, these fast reactors can do is they can take some of the other long-lived radioisotopes that you find in the fuel, and by exposure to the neutron flux, they can transmute them into other radioactive products that have much shorter half-lives, and we go from hundreds or even thousands of years down to 25 or 30 years. They can be stored for a short period of time, then they will be saved. So there's a lot of technology out there. It really is a matter of the will to apply the technology. And of course, the last thing, how many of you are familiar with a place called Yucca Mountain? Okay. Well, Yucca Mountain is a place in Nevada. And a number of years ago, the Department of Energy decided that we need a place to dispose of spent nuclear fuel. So after a lot of research and geological evaluations and whatnot, they picked out a space that they believed would be an excellent spot. They went to the various utilities that were producing this fuel and applied to them a tax. And the tax was used to generate the money to build the Yucca Mountain Depository. Okay, so we have a lot of utilities out there now that have paid all this tax money in to the federal government to build this location. Well, the location was finished, and as far as DOE was concerned, it was a satisfactory location, but due to political moves of people in Nevada, particularly Harry Reid, okay, we were not able to use that facility. So what happened was each individual producer of spent fuel keeps that fuel on site, and they do that in a system called dry cask storage. The nuclear fuel bundles are placed into these cylindrical devices, which are made up of steel and concrete, and they're mounted on concrete pads. And the external radiation is at a safe level, but it's going to have to sit there for a long time.
I actually have two questions. So I understand one technology that is being explored is large-scale storage of electrical energy, and so I wonder if you can say anything about these storage projects that would help to even out the peaks of demand. And the second one is about the effect of the cryptocurrency data farms in increasing our electrical demand.
Okay. Well, as far as cryptocurrency goes, I know nothing about cryptocurrency, but I consider that to be just part of the regular data center issue where you've got a big building of computers and you've got to find a way to power it. And that's why we've gotten into this position where we're requiring the people that build those to generate their own electricity on site. And that's what the recent executive order will require. And the previous question was, refresh me? Storage of electrical energy. Yes, there are a number of technologies out there for storing of electrical energy. And, they're very effective for doing it, and I would put them in as part of the mix. But they're not a panacea, they're not a solution. They don't replace the need to generate baseload power.
In the middle 1980s, the state of Illinois got 51% of its electricity from nuclear sources. How does that compare with the present, which is 40 years later?
Well,
for the state of Illinois.
Yeah, well, that's a good question, and I'm going to have to say I don't know the answer to that question. I didn't turn that one up in my research. Although the state of Illinois still has a number of very active nuclear generating plants. They have the Clinton plant, which is a single unit boiling water reactor. We have 1 unit at Dresden. We have 2 units at LaSalle, 2 units at Braidwood, 2 units at Byron, and 2 units at Quad Cities, and they're all still operating. The Zion plant did shut down. So I think we're getting a lot of our electricity there, but I can't give you a number.
Are there any long-range projections of potential sources? I mean, I'm thinking of highly speculative things, for instance, solar arrays in outer space, beaming energy down.
Well, you'll have to ask Elon. I think he's probably the guy. He's probably the guy for that. I know he wants to put data centers up in orbit and power them with solar radiation, which sounds like a good idea. I wouldn't bet against Elon, because nobody thought that he could have rockets that launch satellites, and you could reuse them 25 or 30 times. So who knows? That may come. Right now, I think the biggest hope we have is that we're going to see a breakthrough on fusion. And there's been a lot of money invested both here, in France, Germany, and particularly the Chinese. I said the Chinese are building a lot of nuclear plants, they're building a lot of coal plants, but they're also investing a lot of money in fusion power.
In light of what's going on in the wars that we've got going on right now and the vulnerability of the grids of the energy and how that would affect pollution and contamination, is that factoring into any of our plans? Because we are as vulnerable with drones today as any other place on Earth.
The answer to the question is yes, we are vulnerable. And I don't know particularly what steps are taken, but I suspect they're probably inadequate.
Is there any talk about what some people are perceiving as this continual growth that we're doing in this country? That we have to stop seeing the continual growth needs and necessity?
That's more of a political question, I would assume. As the demand for services and technology grows, we either choose not to or we provide the power to do it. And my research was based on trying to figure out what power we have and what options we have for the future. Thank you.